Hi guys, I'm Brittany.
And I'm Nadya.
And I'm Ben.
And we're doing Suffix Trees. Suffix trees were first introduced in a paper called Linear Pattern Matching Algorithm by P. Weiner. In this paper, Donald Knuth characterized as Algorithm of the Year in 1973. This algorithm was later simplified by E. Yukonin and Edward M. McCreight. Yukonin actually provided the first linear time online construction of suffix trees, and this is now known as Yukonin's algorithm.
So first, what is a suffix tree? A suffix tree is a compressed trie of n strings that are suffixes of n character string. A trie is a tree structure where nodes represent one character and the root represents a null string. A suffix tree can be constructed in linear time and can be stored in linear space. Instead of allowing for repeated sequences of characters in a string to be represented multiple times, a suffix tree only allows them to be presented explicitly once. An extra character, called a sentinel, is added to the end of each leaf of the suffix tree to ensure that every suffix extends a terminal node. This sentinel character used in our presentation is a $sign. In general, a suffix tree is extremely useful because it allows for fast implementation of many important strings.
So in order to build a suffix tree, the first thing that you need to do is get all the suffixes down. So for our example, we're going to use the word Mississippi. So next, generate all of the suffixes of the string Mississippi. Next, what you want to do is you want to alphabetically order all of these substrings. While not necessary, it helps when you're creating suffix trees by hand. Now that we have all of our suffixes, we can start to build our tree. First, we'll start with our root node. And in order to build the tree for Mississippi, what we do is we start with the first letter and we add that into the tree. So first will be M. The next letter that we have is I, so we're going to add I off of M, and we're going to add it as its own leaf as well. The next letter that we have is S, so we can add it to both MI, I, and we can make it its own leaf. The next letter is going to be an S. Since we already have an S, all we have to do is add it to the tree. The next letter that we're going to add is an I. Since an S is followed by an I and an S is also followed by an S, we're going to have to create a split. So from S, we're going to create another leaf with an S, since S is followed by S. And we're going to create another leaf, I, since an S can also be followed by an I. The next letter that we're going to add is an S. Since S comes after I or comes after S, we already have that in our suffix tree, so we can just add that on. The next letter after that is I. Since I has also been done before, we can just add that on. The next letter that we're going to add is an S, which follows an I. Since we already have an S that follows an I, all we have to do is add it. The next letter that we're going to add is another S. Since S always comes after an S or an I, which we have also already covered, we can just add it again. The next letter that we're going to add is an I. Since I always comes after an S or two S's, which we already have, we're just going to add it again. The next letter that we're going to add is a P. Since P comes after an I, we're going to have to make some changes, because I can have multiple things that come after it. We also need P. The next letter that we have is a P. Since P can only come after another P or an I, we can just add it. And the last letter that we need to add is an I. Now, since I can come after P, but P can have another P or an I come after it, what we need to do is split off of this two P's up here. After that, we can just add it to the rest. Here we have our completed suffix tree. I did add the empty string at the end of every leaf because the empty string is considered a suffix of the word Mississippi. The time that it takes to create a suffix tree is dependent upon the size of the alphabet. If the alphabet is constant sized, the creation time will be linear, since Yukonen's algorithm allows for constant insertion time. If the alphabet is a variable length, the creation time will be n log n. Before Yukonen's algorithm, creation time was n squared or even n cubed. Searching for a substring in a suffix tree takes linear time based on the length of the substring we are searching for. The complexity is linear because the worst case occurs when every letter in the string is unique, creating one long path in the suffix tree. Combined, all of the suffixes take n squared space. However, in a suffix tree, this can be reduced to linear time. The number of leaves is equal to n, where n represents the number of characters in the string, including the sentinel character. Because there are n leaves and at most n internal nodes, the worst case complexity for storing the nodes is O of n plus n, which equals O of n. The number of edges is 1 less than the number of nodes, meaning that at most there are 2n minus 1 edges. Edges can be stored as ordered pairs. The first integer in the ordered pair represents the index of the first letter of the subsequence represented by the edge. The last integer in the ordered pair represents the index of the last letter of the subsequence represented by the edge. Therefore, at 2n minus 1 pairs would have to be stored to represent the edges. This is still worst case O of n, so the entire space complexity of the suffix tree is O of n.
Since suffix trees are a type of trie, they share the same advantages and disadvantages. For example, they can be more advantageous than other data structures like hash tables in the following ways. Looking up data in a trie is faster in the worst case, O of m time, where m is the length of a search string. There are no key collisions in tries, whereas there can be in hash tables. There's also no need to provide a hash function, and a trie can provide an alphabetical ordering in the entries by key. Furthermore, tries avoid redundancy when representing strings with common substrings by only representing them once in the tree. Some disadvantages of suffix trees with relation to other data structures, again such as hash tables, is that they can be slower than hash tables for looking up data, assuming that the hash table has order 1 lookup. Some keys, such as floating point numbers or strings without common substrings, can lead to long chains of characters that are not particularly meaningful. And lastly, some tries can require more space than hash tables, as memory may be allocated for each character in the search string.
Some applications of suffix trees include exact matching, finding substrings, repetitive structures, DNA contamination, genome scale projects, longest palindrome, suffix arrays, longest common substring, and pattern matching. The image is an example of how DNA can be represented in a suffix tree. This is because DNA and protein sequences can be modeled as strings of characters. Natural language allows there to be well-defined sentence structures and word boundaries, but DNA and protein sequences do not have these properties. Because of this, using other data structures typically used for strings such as hash tables is unappealing. Instead, a suffix tree is preferred.
Alright, so for this example, we're going to go over the string banana, and over here, each character in banana has a position index from 0 to 6, including our terminating character. And this is what our suffix tree looks like. So what we need to do is basically take advantage of what's called suffix arrays. And the whole idea behind suffix arrays is that you take all the suffixes of the string, you order them lexicographically, which basically just means alphabetically, and then you take their indices. So here we have our ordered suffixes, and what we have done here is we take their corresponding position in the string banana. We store these in an array. This thing is our suffix array. So it's just an array of integers, and it corresponds to these suffixes. So we don't want to store these suffixes because they're quadratic space with relation to our original string. So we don't need to store that. So next what we need to do is come up with an auxiliary array called an LCP array. An LCP stands for longest common prefix. So what we want to do is get the length of the longest common prefix between each adjacent suffix in these suffix arrays. So what we're going to do here is we're going to start comparing these side by side. So between $sign and $, there isn't any common prefix, so they get a 0. Between $sign and $, they have a prefix A, which is of length 1, so they get 1. Now this auxiliary array is our LCP array. So the claim here is that using these two arrays, these two pieces of information, we can construct this exact same tree. What we're going to do next is we're going to use something called a Cartesian tree, and you're supposed to take your minimum elements in your LCP array, and you're going to throw them at the root. So we're going to have 3 zeros at the root of our LCP tree, Cartesian tree. And next, we're just going to go one by one in the elements and throw them into available slots in this tree, in this binary tree. All we're really missing here is the leaves. So we can, that's represented by our suffix array. So we can go ahead and just start filling those out, do like an in-order traversal. So basically from this, we can construct this tree, minus obviously we have to still put in the labels, but we won't cover that here.
One of the most common problems used with suffix trees is the exact pattern matching problem. For example, given a string S and pattern P, where S and P are sequences given over an alphabet, either ASCII, Unicode, etc., find all occurrences of P and S. The solution is to first start from the root and then search all the edges of the suffix tree from the root for the first character of the pattern. If there is no edge, then the pattern does not occur in S. If all the characters of P were found in order, then P is found in S. The animation shown demonstrates this process. The animation is looking for all occurrences of NA in the string bananas. First, it searches the leftmost node for the pattern NA, but finds only a sentinel character with no children. Then it searches the next leftmost node, A, and finds that it has 2 children, a sentinel character and the pattern NA. Then it searches again to look at the children of this. It sees that NA has 2 children. Another child is NA also, and a sentinel character. This shows that there are 2 occurrences of the pattern NA in the word bananas. One important thing to note is that in a suffix tree, the edges actually contain the data for the characters, and the nodes contain the data for where the position is in the string.
In general, suffix trees are very fast and efficient data structures for storing the suffixes of a string. Suffix trees can be built and searched in linear time thanks to Yukonin's algorithm. They are very good for doing pattern matching on strings and are commonly used in DNA research.